All right, today we're going to look at probabilities of disjoint and overlapping events. So first of all, we need to talk about what's called a compound event. So the probability of a compound event, combines at least two simple events, either the union of two simple events or the intersection of two simple events. So let's go back and review for just a second what a union and an intersection is. So if you look here, if you have two sets, so you have an A and a B set, if you have a union is going to be an OR. Okay, so this guy, this OR right here, is designated with this symbol right here. Okay, so that OR is that symbol. Okay, it looks like a U, regular U. A union simply means everything. Okay, so it means everything here that's in A, so we'll label this one A. So all of this is A. And what's in B here. So all of here, what's in B. So it's literally everything, okay? Now an intersection is an AND. So here we have and notice the symbol is an upside down U, okay? So that is an and is only where they overlap. So again, if this is set A and this is set B, it's what they have in common. Okay, so this is what they have in common. So when we're talking about a union or an intersection, or an or an and, this is what we're talking about. Okay, so if we're looking for the probability of something or something else, we're looking for all the possibilities. If we're looking for the probability of something and something else, then we're looking for just the center. So today we're just going to look at our ORs, so mostly just our unions, but you need to know these symbols, okay, because they're going to come up. So OR compound events, we have two types. We have one that's called overlapping, and we have another which is called mutually exclusive or disjoint. So overlapping have a common outcome. So like in here, this picture here, you can see that these four options for the probability are included in both sets, in A and B. Okay, so this is overlapping when they have a common outcome. So for example, if you think of like if you're rolling a dice, okay, a die. So you have options 1, 2, 3, 4, 5, 6. If I said you're going to find the even numbers or the number 2, okay, number 2 is an even number, so they overlap. Okay, so that's why they're considered overlapping. They fall in both groups. Now, mutually exclusive, also called disjointed, okay, so disjoint or mutually exclusive, they mean the same thing, have no common outcome. So notice that these two groups, this group A and this group B, is completely separate. They have nothing in between them, no common outcomes, okay? So let's look at an example. So we have the spinner shown, and it's been divided into 8 equally sized sectors of a circle. So it's important that they're equal because that means they all have the same chance of happening. So you have an equal likelihood of getting a 1, as a 5, as a 7, as an 8, and so on. Okay, the spinner is going to be spun one time. In this experiment, we will let A be the event of it landing on an even. Okay, so we're going to say A is even. And B is the event of it landing on a prime number. So B is a prime number. Okay, so we're just going to kind of mark these down so we can keep this track of this. So the first thing we're going to do is we're going to fill in the diagram below with the numbers from the spinner. So A is evens. So our even numbers, of course, are going to be 2, 4, 6, and 8. Okay, so those are our even numbers, 2, 4, 6, and 8. That's going to be our evens. And our prime numbers, remember prime is defined as being divisible by itself and a number 1. So the number 1 is actually not prime, okay? It can only be divided by 1, and it is itself 1. So it actually has to be divided by two numbers, 1 and itself. So in this case, 2 is also going to be prime. So 2 is prime, 3 is prime, 5 is prime, 7 is prime, 4, 6, and 8 are all composite because they can be divided by something other than 1 itself. 4 can be divided by 2 and 2, 6 can be divided by 2 and 3, and so on. So now let's fill in our Venn diagram here. So what do they have in common? They have this 2 in common. So the 2 is going to go in this intersection part of what they have in common. So then the even numbers that are in A that are not prime would be 4, 6, and 8. Okay, so our even numbers 4, 6, and 8, they're not prime, but they are even. Our prime numbers that are not even are going to be 3, 5, and 7. So here is our diagram. This is going to help us see what we're doing. So they want us to find the probability of A. Now remember, that's a union. So union means or. So this means or. The probability of A or B happening. Okay, so if we look at this, A or B happening, we have 1, 2, I'm going to circle them so you can see. We have 1, 2, 3, 4, 5, 6, 7. So there are 7 opportunities to get an even or a prime. So we have 7 out of 8, which if you were to divide this, if you wanted the decimal, that would be 0.875, or if you wanted the percent, that's 87.5%. Okay, now I did forget to put in my sample space the number 1. 1 is still out here. It's just kind of hanging out here on the outside. It doesn't fit in either one of those, okay? So there are 8 possibilities, 8 even spinners. So we have 8 pieces here. So there's one possibility of that not happening. Now we want to look for where A and B. So remember, this is an intersection. So this is and. So where is A and B going to happen? Well, that only occurred here, this one chance. So that's going to be 1 over 8 total possibilities, which if you divide that is 0.125 or 12.5%. Remember, they can be written as a decimal fraction or a percentage for probabilities. Okay, so this is looking at our unions and our intersections, just so you have kind of an understanding of what we're looking at here. Okay, so now let's look at a little bit more. So a card is randomly selected from a standard deck of 52 cards. Okay, so if you recall, there are 52 cards in a deck. There are 4 different suits. So we have hearts, we have clubs, we have diamonds, and we have spades. So spades and clubs are black, hearts and diamonds are red. There is 1 through 10, and then there's a king, a jack, a king, and a queen for each suit. Okay, so 13 cards in spades, 13 cards in hearts, 13 in diamonds, and 13 in clubs. So that's where they get 52. 13 times 4 is 52. So first of all, they say, what is the probability that it is a 10 or a face card? So probability of a 10 or a face card. That's what we're trying to figure out. So there are 4 10s. There's a 10 of diamonds, a 10 of spades, a 10 of hearts, and a 10 of clubs. A face card means a jack, a king, or a queen. Okay, so 10 does not fall in jack, king, or queen. Jack, king, or queen does not make them a 10. So they want to know, is this an example of an overlapping event or a mutually exclusive event? Because they do not share any possibilities in their probability, this is going to be a mutually exclusive event. I think I just spelled that wrong. Sorry. Okay, so they have no common possibilities here, no common things, nothing in common. So now they want us to find the probability of 10 or a face card. Okay, so again, when we're thinking this through, there are 10 possibilities of a face card. So the probability of a face card is going to be 4 out of 52. And there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 possibilities of a face card. So 4 possibilities of a 10. So this is probability of a 10. And this is probability of a face card. And so total, altogether, we would add those together and we would get 16 out of 52, which would simplify down to 4/13. So we would simplify that down. Or you could even say that as a decimal is 0 about. Okay, it's not exact. About 0 point, I think it's 308, something like that. Okay, so the decimal or the fraction is fine here, but it's about 4/13. 4/13 is the probability. Okay, and you can count it. We can see we can count. If we sit here and count all these options, 10, 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there's 16 possible outcomes out of the 52 cards. Okay. Now they want us to come up with a general formula. So this is the formula so that we don't have to write out the sample space every time. We don't have to show this Venn diagram. So what we can do is we can see that when we have a mutually exclusive event, okay, so let's write that down. So this formula is only for mutually exclusive. We simply add the probabilities together. So when A or B, so A union B, this simply is P of A plus P of B. So you add the two probabilities together because they have no overlapping, nothing in common, okay? So let's look at another example. So a card is randomly selected from a standard deck of 52 cards again. What is the probability that it is a face card or a spade? Okay, so this time, face cards and a spade, well, there are 3 face cards that are also a spade. So if you notice in this diagram, we have a king, a queen, and a jack that are all spades. This is an overlapping event. Okay, so this is overlapping because they share a common outcome. Okay, if they share a common outcome, it's overlapping. So this time it says find the probability of the face card, of a face card and a spade. So to do this, let's see, let's count up all our face cards. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Remember we had 12 face cards out of 52. Well, how many spades do I have? Well, if I look here, I've got 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I have 13 out of 52. But if I do what I just did, like I add them all up, I have 25 outcomes. Well, let's see if I have 25 outcomes here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Notice I only have 22 outcomes. So how did I get that 22 out of 52? What happened? If I add these together, I get 25. Well, hopefully you notice that I counted the king, queen, and jack twice. I counted them as part of the face cards, and I counted them as part of the spades. So what we have to do is we actually have to subtract those 3 cards that I counted twice, because I can only count them once. And notice that when I do this, I end up with 25 minus 3, which is 22 out of 52. So that is where we have to be careful when things overlap. If they share a common outcome, we have to deduct it because it gets counted twice. So again, if we reduce this down, we would have 11 over 26, which is about 0.423 if you were to divide it. Okay, so decimal or fraction is fine. Now, again, we're looking at a general formula. So what is the general formula for this type of event? So again, this is for overlapping. So to find an overlapping event, so when P of A or B is overlapping, you do the probability of A plus the probability of B, but then you have to subtract the probability of A and B. So this is and, don't forget, that's and. Okay, so you have to subtract the probability of A and B, so what they have in common. Now, really, you can think of this could be your one formula right here. This guy right here is perfectly acceptable because what you could do is say, well, if it's not overlapping, they have 0 of an and. So you could just say P of A plus P of B minus 0. Okay, so if it's not overlapping, if it's mutually exclusive, you could still use this formula, but you would put 0 in for the and. Okay, so let's look at a situation. It says you are performing an experiment to determine how well plants grow under different light sources. Out of the 30 plants in the experiment, 12 receive visible light, 15 receive ultraviolet light, and 6 receive both visible and ultraviolet light. What is the probability that a plant in the experiment receives either visible light or ultraviolet light? So here's what we're trying to find. Here's our probability. So the first thing I'm going to do is write that down. So what am I trying to find? The probability that an experiment receives either visible light, so visible light, or ultraviolet light. So I'm going to put UV for ultraviolet light. Okay, so this is what we're trying to figure out. So I'm going to write down all that stuff they told us because it kind of got a little bit lost. So the probability of visible light is going to be 12 out of 30. So remember they told us there's 30 plants. So the probability of UV light is going to be 15 out of 30 because they told us 15 of the 30 plants had it. And then the probability of visible and UV, right? This is and, is going to equal, what do we got, 6. 6 out of 30. So the first thing we have to decide is this a mutually exclusive or an overlapping event? So to do this, let's think this out a little bit. If we had 12 plus 15, that's what, 27? Right? So if we were to add 27 plus 6, that's 33. That's more than we have. So most likely this is going to be an overlapping event. The other way we know is that the fact they tell us this is an and. So remember, we have our probability formula, which says P of A or B equals P of A plus P of B minus P of A and B. Okay, if this did not exist here, if they didn't have 6 receiving both, then that would be 0. Okay, so we know this uses this formula. This is actually going to be an overlapping event. There's an and involved. So we're going to fill this in. We're going to use our formula. So we've already found the probability of visible light. That's 12 out of 30. We found the probability of UV light, which is 15 out of 30. And now we just have to subtract where they overlap, 6 out of 30. So 12 plus 15 is 27. 27 minus 6, 21. Hopefully. So 21 over 30, which would simplify down to 7 over 10. Or if you really wanted a decimal, that would be 0.7 or 70%. So I'm going to keep the fraction. 7/10 is fine, but either one. They don't really tell us how to write it, so unless the directions say otherwise, you can write it however you prefer. Okay, so that is it on this lesson about disjoint or mutually exclusive and overlapping events. So if you go ahead and try the problems, and that's it.